Now, let's let's start with Heisenberg's uncertainty principle and try to recap the things that we have done till now in terms of matter waves and the predictions based on de Broglie uh, and confirmation of wave nature of electrons. Now, uh, if I have to make sense out of this nonsense. Uh, this is not nonsense. This is the only principle in physics that tells us no, you cannot do that, and that's the beauty of this principle, and this is what makes it unique that you cannot, and it certainly prohibits us of doing anything that humans can think of. Now, Now about de Broglie waves, we have the wavelength, and wavelength is h by mv. Now this is a monochromatic wave of infinite extent, right? And and the phase velocity uh, of such a monochromatic wave. So monochromatic, we understand now. It's a monochromatic. It's a monochromatic wave. So the phase velocity of this monochromatic de Broglie wave it is nu lambda, and we can see that is if we make use of h nu and we make use of h by lambda, this will be E and this will be momentum, and this will be mc squared, and this will be mv, and this will cancel and we will have c squared by v. So this phase velocity is c squared by v when we take a monochromatic wave. And and uh, thus, I would say that this the velocity of this monochromatic wave is always greater than the velocity of light in vacuum. Now, therefore, I can say that it is theoretically impossible for a monochromatic de Broglie wave train to transport a particle or carry the energy. So the phase velocity, it merely represents the rate. It designates, it describes the rate at which a given phase of a monochromatic wave train advances, and is purely a mathematical concept. And and talking about the stability of a material particle like electron, it demands that it should be concentrated. It should be concentrated over a small region. Of space, and at any given instant of time, it should be within that domain of small volume, and thus the mass and the charge of the particle, like that of electron, these are localized entities. It has charge, it can be localized. It has mass, it can be localized. However, when we talk about the de Broglie wave, with which we represent, which will represent this moving particle, is of infinite extent by virtue of being monochromatic. That I will repeat the word monochromatic here. So so what becomes essential here is that what we do is we take a group of waves of nearly equal lambdas centered around this de Broglie wavelength, lambda equal to h by p. And when we do this, what we obtain a wave packet and the amplitude of which is different from zero only in certain regions. If we go back to the previous one, so you have the amplitude of the wave where we have the nodes and where we have the probabilities. So we have the nodes. So, so there are certain small regions of space having dimensions of the particle. This small region of space is associated with the position of the particle, and this wave packet travels with the velocity known as group velocity, and we have proved in the last video that this group velocity is equal to the particle velocity. So this group of waves is associated with this particle. It is within that limited volume that this particle has. So what can we say, how can we further move in this direction, is that instead of associating a single monochromatic de Broglie wave with a particle, what we do, we associate a group of waves, right? And this group of waves that we associate, it forms a wave packet consisting of group of waves of nearly uh, equal amplitudes, centered around de Broglie wavelength lambda of the particle, right? So this association of what we associate this so we are again coming back here to group velocity, the group of waves. Now this association of waves that we have that we have with the moving particle means that the position of the particle at any instant of time cannot be specified with desired degree of accuracy. With desired degree of accuracy. All that we can talk about, all that we can say is that the particle is somewhere within this group of waves. That is within this small region of space. Thus, thus a certain inaccuracy will always be linked. That the certain inaccuracy will always creep in in the position of this moving particle, like the electrons, protons, etc. And with similar reasoning, it can be argued that a certain amount of inaccuracy will again creep, will again develop in determining the velocity and hence momentum. So there will be creepy situations for both position and momentum. For a particle which is enveloped by these group of waves that are linked with it. So on the basis of this argument, Heisenberg stated a principle known as Heisenberg's uncertainty principle. Now, what does this principle tell us? It tells us that uh, that that I should say that it states that in any simultaneous situation, it uses the word simultaneous situation, determining the position and momentum of the particle. I mean, the product of the uncertainties of position, suppose delta x is uncertainty in determining the position, and delta p is uncertainty in determining the momentum. The principle says that the product of this uncertainty in the measurement of position and uncertainty in the measurement of momentum should always be greater or equal to some minimum value. And what's that minimum value? That is Planck's constant. And in this situation, for a motion of a particle along x-axis, where delta x is the fundamental error, you have a particle moving along x, and this delta x is the fundamental error or uncertainty, I can say, in the measurement of the position. And this delta p is the fundamental error or uncertainty in the measurement of momentum or velocity. And the more accurate calculations give us that this delta x, this delta p is greater or equal to 1 by 2 h by 2 pi. As we know that this h by 2 pi is h bar, so to to write down uncertainty principle, this delta x, this delta px is greater or equal to h cross by 2. Now, according to the classical ideas, if we talk about the classical ideas, it is possible, it's exactly possible for a particle to occupy a fixed position and have a definite momentum, and we can exactly predict its position and momentum at any instant of time. At any instant of time. At any instant of time. Later on, if we know the initial conditions of this particle. But when we go into the domain of microscopic world, it is not possible. According to Heisenberg, it is not possible to determine accurately the simultaneous values of position and momentum of a particle at any time. If it is desired to reduce the error in determining the position, that's to reduce this delta x, then this can only be done at the expense of accuracy in determining delta p. And this will automatically increase the error in the measurement of the momentum. If we try to reduce the error in the measurement of position, it's gonna automatically increase the uncertainty in the measurement of the position. That should be the case. That should be the case to determine. So it seems to be an intrinsic behavior associated with this microscopic particle, who is enveloped by these group of waves surrounding this particle. So this Heisenberg's uncertainty principle, it's applicable to all those conjugates. Conjugates. It has to be J here. I'm sorry, I don't have a very good handwriting. I have repeatedly spoken about it, but I'm trying my level best to make things appear at least they can be recognized. So this Heisenberg's uncertainty principle is applicable to all those physical quantities, to all those pairs which are conjugates or complementary pairs of physical variables, and the product of which has the dimensions of. The point is dimensions of this Planck's constant. So we can immediately say that this delta x and delta p, it has the dimensions of Planck's constant. And it has, we can check it immediately. This is meter and this is kilogram meter per second square. And that will give us joule second. And we can have another pair, say energy and time. So they are the conjugates of each other because the product of their dimensions will give us the dimensions of Planck's constant. And same will be true with some angle and some angular and the angular momentum. So all those pairs which are conjugates, that means when you multiply the dimensions of those pairs A and B, if you get the dimensions of Planck's constant here, they are the conjugate pairs, and this principle is exactly valid for those pairs, stating that it's impossible to accurately measure the position and the momentum of a particle simultaneously along x direction. So if we proceed from here a little bit more and and try to investigate in more detail, go into the conjugate pair of energy and time. So what I said here is that delta E, delta T, they must exactly hold that they are greater or equal to h cross by 2. Now, suppose I suppose I choose a particle, and this particle is moving with the velocity v. I can immediately talk about its kinetic energy as 1/2 of mv squared. Right now, in order to measure the uncertainty in the measurement of energy, I will take its delta. So this delta ek will give me 1 by 2 m. So 2 will come down to v, then we will have delta v. This 2 and 2 will cancel. So this delta ek, the uncertainty in the measurement of energy, will be mv delta v, right? That should be the case. So if I take this, since this is a non-relativistic case, I can take this m inside. So this will be v delta p, because p is p is mass into velocity. Right now, if I define if I define the velocity as the small change in delta x, so uncertainty in delta x by delta t. So this is my velocity, delta x by delta t. So I can immediately use this equation in above. So what I'll get delta E equal to delta x by delta t and delta p. This is what it looks like. All right. I think there's no problem till now. Now, if I have, what I have is, I know that this delta p and delta x, what is it? It's greater or equal to h. So I can write delta E is, what is it? Instead of this, I'm going to use that h bar greater than this. So I will use this greater or equal to h by delta t. So what will I get? I'll get delta E, delta t is greater or equal to h. And if we do the calculations in more accurately, we will be able to find that this delta E, delta t is greater or equal to h cross by 2, where h cross is what it is h by 2 pi. So we can see here that uh, that uh, uh, that uh, that uncertainty principle is equally valid for energy and time. And if you see the dimensions of product of energy and time, you're going to get the result will be the unit of a Planck's constant. And we have chosen delta E as the error in the measurement of energy and calculated that error by taking the derivative. And we have finally come up with an equation that tells us that we cannot simultaneously measure energy and time associated with a microscopic particle. The uncertainty in the measurement of energy times the uncertainty in the measurement of time is always greater or equal to some fundamental quantity, and that is h cross by 2.